just watching on recording. I did go through your final exam that we have on Friday for the classroom portion of this course. It is 80 questions. I did remove the math questions from it, which is why it's only 80 questions. There was a bunch of math questions on there that I just wasn't happy with seeing on there, so I did pull those out. So you don't have to worry much about that. But again, it's an 80-question exam. Nothing we haven't talked about in our lessons as well as you had in your reading. So that's Friday's exam. I don't think any of you, if you've been watching the lectures, my online sessions, and doing your readings, I don't think any of you will have a problem with it. It's pretty straightforward. Just know series and parallel circuits, understand voltages across open-closed switches, understand what a coil of wire does, and I think you guys will be fine. And again, you have two attempts on it. First attempt, try to do it on your own. Second attempt, you can use resources. That way we all know that, you'll get the higher grade. So that's one thing. The other thing is, I know a bunch of you have sent me email messages regarding specific assignments. I did catch up on the grading last night of what was submitted in the courses, but I did not get through all my emails. I will get to them this evening, okay? So I'm not ignoring you. I know you have sent me emails on some stuff. I have not. It's not that I'm ignoring them. It's not that I didn't get it. It's just that I ran out of time last night. The third thing that I need to mention, and I can't sort of believe I'm having to mention it this late in the term or in the course, down on the bottom of the left-hand side of the web browser, okay, and again, I'm talking about the browser. I think in the app there's also a place for either school links or student links. On that school links, there is a place for ebook and app code orders. Okay, if by chance, again, hard to believe, you don't have one of your books yet, click on that link for ebook and app code orders. Go in here and, don't use my information. It won't do you any good. But go in here, fill out your information on your student ID number, okay, your school email address, your first and last name. Click Submit. Click for the ebook order system. Okay, and then submit and finalize and place your order. That's how you get any missing books you might not have. Okay, I got a couple emails on math books missing. You know what? Go in and order your books. Okay, if you've already done this before, you might need to update your bookshelf on Vital Source or whatever. Okay, I got a ton more books than you will ever need because I get all the programs. But again, go through the links. This is a self-service environment, and you can get any missing books. Okay, so that takes care of that. Okay, anyone have any questions before we begin the material I need to cover today? Okay, now. Today I really want to talk about starting relays, and I have to talk a little bit about your gauges. We call them manifold gauges. It's your AC gauges. We got to talk about both. I'm going to start with the starting relays, okay? Because if we do not finish the gauges, I may ask you to watch a video, to watch the remainder. There's a lecture video on them that's pretty decent. So I'd rather spend some time talking about starting relays. Now, we've talked a little bit about starting relays before, okay? We've talked about them when we were talking about motor windings. A starting relay is like a potential relay. Basically, the whole purpose of the starting relay is to take the start winding out of the circuit once the motor has started. If there's a start capacitor, that start capacitor cannot be left in the circuit once the motor has started. There's also one type of motor that we don't leave the start winding in the circuit once the motor has started. Can anybody tell me what type of motor that I do not leave the start winding in the circuit? Was in your reading. Anybody?
It's not the permanent start capacitor, is it?
No, permanent split capacitor, or PSC, is the one motor that the run capacitor, it doesn't have a start capacitor. The run capacitor is always in the circuit. But there's one motor that doesn't have a capacitor that we take the start winding out of the circuit. Anybody? The split phase motor. The split phase, the basic split phase that doesn't have any start capacitors. We take the start winding out of the circuit using, most often, a centrifugal switch. And I'll go into that in a moment. But it comes out of the circuit about 75% of the run speed. Once the motor reaches about 75% of normal speed, that centrifugal switch opens and the start winding comes out of the circuit. So again, I just want to mention that most, with the exception of that one motor, the purpose of the start relay is to take the start capacitor out of the circuit. Okay, we have a whole bunch of different motors. Okay, if you look at it, this is all air conditioning motors. They're all compressors. We go from the little scroll type compressors. We have our centrifugals. We have our reciprocating, the big beasts that we can take apart, the semi-hermetic. We haven't talked about them much yet, but all the pieces come apart. This top one is the one I told you I skipped yesterday. It's the older style reciprocating compressors. Looks like what you would see in a car engine. Okay, you have the pistons that move up and down. We have valves up top that open and close and allow the refrigerant to only flow in one direction. Okay, so all of these are motors. We got to start them. We got to start them safely, and we got to start them without blowing breakers and fuses. Okay, in all of our compressors, you only have one access point to the motor windings in compressors. Okay, and it's down the outside of the compressor. Everything else with the motors, everything else with the windings is actually in the refrigeration circuit. So this is your only access point on the side of compressors. Okay, sometimes they're labeled, sometimes they're not. Okay, which is why I went over a while ago trying to figure out what is our start, run, and common winding. My highest resistance is always, again, across from the common, because we go basically run, start, common, and start is the winding setup. So again, this is your only access point. So the purpose of our starting relay is to remove the start winding and or start capacitor from the circuit. Compressor start relays are always mounted outside the motor. A centrifugal switch, which is that one component that I told you is on the smaller motors, on the split phase motors, cannot be used in a compressor. Basically, a compressor is a hermetic motor. Hermetic just means it's sealed inside a steel container. Okay? These are the three most common types of relays that I'm going to go over. Okay? The horsepower of the motor determines what type of relay will be used. Okay? The service person, your technician, may not replace. Okay, may replace but not redesign. We don't want you guys becoming mechanical engineers. We want you replacing the existing part if it goes bad. Okay, I don't want anyone redesigning motors. Neither does the manufacturers. It's a great way to break warranties. Don't redesign things. Replace what's already there. We have three types of relays. We have a current coil. We have a solid state, otherwise known as a PTC. Can anyone tell me what PTC stands for?
Positive
partial time circuit.
temperature coefficient relay.
Yeah, it's a positive temperature coefficient, which basically means the resistance of that relay increases as the temperature increases. Positive temperature coefficient. The resistance, and I'll go more into this, but the resistance increases as the temperature increases. No moving parts. That's the great thing about this relay. No moving parts. And then finally, we have the potential relay. Okay? The current coil relay is the only relay that we wire in series with the run winding. Okay? This is critical. The current coil relay is the only relay you will ever find that's wired in series with the run winding. Remember, I told you we don't wire loads 99.95% of the time in series with other loads that are in the 120 volt 240 side. Okay, we want everything to get full voltage. The current coil relay is the one exception. On any motor starting up, especially compressors, when you first turn the switch on, the motor draws a very high current. That induces a very strong magnetic field in the relay's coil that's wired in series with the run winding. The magnetic field lifts the plunger and the contacts to the start winding are made. The start winding is energized. So again, this works with a coil that's wired in series with the run winding. This is extremely important. So on your current coil relay, this, where I just drew arrows, that actually slides onto the pins of the compressor. Okay, and these are gravity sensitive. So in other words, they have to be mounted right side up. There's a solenoid coil down here at the bottom and a spring. When the run winding pulls a very heavy load, in other words, heavy amperage, this works off of amperage. That's why it's called a current coil relay. It creates magnetism on this coil down here, lifts this plunger up, and closes the contacts. Okay? This is the only relay that is wired in series with the run winding. I'll show you the coil in a second, and I'll explain why we do this. Okay? There's something special about this coil. Now, the way this is wired, okay, we bring in line to our common, and by the way, if you have neutral, that will be neutral and that will just be line. Okay, we have our start capacitor that's wired to the normally open contact. That goes to the start winding. We have our run winding, which is right here, that comes through the coil of the relay and goes back to line. And again, so your coil of this relay is in series with the run winding. It is the only coil you will ever find in series with the run winding. Okay? Now, look at the size of this coil. What can you tell me about this?
It's got a very high resistance.
Tell me about the size of the wire compared with some of the other coils I've shown you.
Seems to be a lot thicker.
It's a lot thicker. Okay, there's less of a coil. So if I have thicker wire and less coil, okay, less turns of coil, what does that tell me about the magnetism that's produced?
It's greater.
Well, it's not very strong.
It's not very strong, okay? The less wire, the thicker the wire, the resistance of that wire as the current goes down is very small. As the current goes up, the resistance of that wire, you remember I talked about inductance? That resistance of that wire, it grows as the magnetic field grows, but it's not a very strong resistance. It's not a very strong magnetic field under normal operation. So because of the size of this wire, when this device is when the motor's regularly running at a standard amperage, let's say it's pulling 3 amps under normal operation, okay, this coil doesn't have much of a voltage drop. There's no resistance to it. The thicker the wire, the lower the resistance in a coil. So we basically have no voltage drop, so it really doesn't even see the coil being there. But when the motor first starts, it goes to what we call locked rotor amps, LRA, okay, which is that initial amperage that it takes to get the motor to start turning. Okay, so as we go through locked rotor amps, this coil starts generating magnetism. The magnetism, it generates also a little bit of internal resistance, not all that much. But it raises this plunger, and it makes a contact from my start capacitor, which is wired in here. Okay, it starts making contact. Okay, and it brings that start capacitor and start winding into the circuit. Again, the coil is in series with the run winding, and you'll see it drawn out sometimes this way. Okay, we have the run here. And then we come down here, we have my capacitor, okay, and we come to our normally open contact, and that connects to my start winding. Okay, and the 2 pins, one of them is run and one of them is start. So the only thing you have to worry about wiring in is the capacitor. Everything else is already there when you put this on here. Any questions on this? Okay. Now, the motor starts because the start winding creates a pretty strong magnetic field. Once the motor reaches about 75% of its run capability, that current starts dropping down. We're no longer pulling locked rotor amps. That relay coil in series with the run winding doesn't have enough current to keep the coil magnetized. This all works on current, not voltage. The spring pushes the plunger back down, it opens the contacts, and the start winding is de-energized. Okay, again, very easy to remember. The current coil relay works on current through the start winding. It doesn't work on voltage. It strictly works on current. Now, can anybody take a guess? And a guess is okay. Are these relays interchangeable? In other words, can you carry a standard one of these relays on your truck? Or is it pretty specific to the compressor?
Yes.
Yes on which choice?
Just yes.
Very
specific.
Okay, I heard someone say pretty specific. What did somebody else say?
They can be replaced.
Okay, it is pretty specific to the compressor, and yes, it can be replaced, but with another type of relay, and we'll go into that in a few minutes. So the problem with the current coil relays, okay, and the reason we've gone to some other replacement options is it is extremely specific to the compressor. Okay, you have to have this exact amount of start current. Okay, you have to have the exact amount of full load current, or RLA, which is our run load amperage, okay, because we can't have something that might not take out the start winding. So when we used to service a ton of these things before the replacements came out, I had a drawer full of current coil relays on my truck. You know, one of those pull-out drawers that is like in a truck cabinet. I had tons of these things because I did a lot of refrigeration and a lot of light commercial stuff that we used a lot of these things for. And when one went bad, I used to have to go search through the supply in the truck, try to match numbers and stuff like that. It was a nightmare to maintain that stock, because if you used one, you had to make sure you got a replacement because it just got bad if you reached for something. So they started to come up with other options, and I'll go into those. But the current coil relay is still used very heavily. It's still shipped on new compressors. When you go back into the shops, take a look at the compressors that are on the refrigeration trainer boards. Okay, those compressors in most of our shops still have current coil relays on them. Do I believe that they're the correct relays for those compressors? No, I think they've been changed out over time and we're just lucky. But you'll see the current coil relays on them. And you'll see the start capacitors there. In air conditioning, the only place I'm now using current coil relays frequently is on window units. The larger split systems, the 1 ton, the 2 ton and on up, you're not going to see current coil relays used unless it's like a 25-year-old piece of equipment. Okay? We just don't use them anymore. So that's where current coil relays are used. They're fractional horsepower compressors for small refrigeration units, and not large AC, okay? You might see them in window units. Less and less as well there. Current coil relay looks exactly like this. Again, you can always tell them because of the size of this coil. Okay? Now, it is extremely important that that you look at the current coil relay, okay, and you can see there's always an arrow that points to the upside. Okay, they are gravity sensitive. You have to mount them properly, because if you mount them upside down, it will always keep the start winding in the circuit. The spring in there is not strong enough to overcome the force of gravity. So just be careful on that. Okay, and again, this is a picture of a current coil relay. And as I said in my last slide, if you have neutral, this becomes neutral, and this becomes line, because I always want to switch line. Questions on current coil relay? Anybody? Okay, solid state relay is the one that I use to replace current coil relays. If I have a current coil relay that goes bad, okay, and if I need to replace it and don't have the exact match on current coil relay, okay, I can use a solid state relay to replace a current coil relay. It also works off current, but it has materials that change its resistance. It's called a positive temperature coefficient. The temperature of the device goes up, the resistance goes up. It's wired in series with the start winding only. Okay, so as the start winding pulls current, okay, and the start winding starts pulling more and more current, it will eventually take that relay out of the circuit. Again, remember, voltage uses the path of least resistance. So as soon as this relay goes up, has a resistance that goes up over the resistance of the run winding, it will start sending all the current through just the run winding. Okay, so it's wired only in series with the start winding. Works off current. Okay, it uses voltage. In other words, if I have my positive temperature coefficient relay, okay, and that's just one of the symbols you can see for it. There's others as well. Okay, you can see it's a resistor, and it's variable. Okay, so there's a bunch of symbols you can see for those. That's a little arrow through a resistor. Okay, so you have a couple different symbols you can see from them. I always just label it PTC, just so people know what it is, because there's so many symbols used for it. But it's wired in series with my start winding. So any voltage that's flowing through to the start winding, goes through this PTC device. Okay, so there's a voltage drop across that relay. Okay, remember, Ohm's law in series, there's a voltage drop. That voltage drop across that device becomes greater the longer it's in the circuit. And I'll show you some examples of this. Solid-state relays have a greater range. Okay, so for example, I can use a relay that's 1 SS. Okay, one solid-state relay can be used for a 1/16 to a 3/4 horsepower motor, and then another one could also be used 3/4 to 2 horsepower motor. Okay, I have a very wide range of motors that I can use on a single solid-state relay. If a current coil relay was being used, I'd have to have different relays for every size motor through here. The current coil can't handle it, but the solid-state can. So again, the solid-state is an awesome replacement for the current coil. Okay, because you're working in motor ranges. When you buy a solid-state relay, it gives you as motor ranges. Okay, right on the packaging. Okay, and the way this is wired in, okay, again, we come in, we have our solid-state relay is in series with our start winding. Okay, run winding gets pure power. Okay, does anybody notice something strange about this diagram?
Yes, the relays after the compressor.
Yeah, this is actually taken off a window unit This is actually taken off a window unit nameplate. Okay, we pulled this from a window unit, this diagram. There's something pretty important here. Does alternating current have a true positive and a negative?
No.
Okay, so in the grand scheme of things, does it really matter if we wire our common to line and our switching devices to neutral? Does it really matter?
I would say no.
Yeah, no is the correct answer in the grand scheme of things. However, from a safety standpoint, which is the way I'd like to see this wired if I were a technician reaching into this? How would I like to see it wired?
The relay before the compressor?
I'd rather have all my switching devices off of L1.
Right.
Okay, because that way I know things are turned off when I turn that switch off. Okay, it really doesn't matter. You're going to see a ton of wiring diagrams this way, but from a safety perspective, I really wish this was opposite. Okay, it's sort of confusing sometimes when you look at these and see it the wrong way, but it really doesn't matter from an operational standpoint because of AC current. But again, the solid-state relay is in series with the start winding. Okay, this is what a solid-state relay looks like on a compressor. Okay, we have this device right here. That's my solid-state relay. Okay, what's this device over on the left-hand side?
It's an overload?
Yeah, it's an overload. What's it sensing? What caused that overload to open?
Off the common.
Yeah, it's on the common, but what's it actually sensing on that common?
The current.
Yeah, as the current gets too great, okay, there's a bimetal switch inside that overload. As the current goes up, it will start heating up and it will actually open that bimetal switch. Now, here's the other thing you have to be aware of. Where it is mounted, does the heat of the compressor affect it? if this compressor gets too hot, yeah, if that compressor gets too hot, that switch can actually open, okay, based on the temperature of the compressor. So just be aware of that, because sometimes it's all you might say, oh, we have a bad one, everything else is working right, but you feel the bottom of this compressor and you can barely touch it. Okay, the problem might not be the overload. It might be that my compressor is getting way too hot, which is a sign of a whole bunch of other problems. Okay, again, when you have a start capacitor with a starting relay, that start capacitor gets wired in series with the solid-state relay. Now, most often, if it's mounted directly to the compressor, this start capacitor will come before the solid-state relay, because if it's mounted directly to the pins, you just don't have that option to put that there. So again, start capacitor is in series with the solid-state relay and the start winding. So if it's drawn out, okay, you have your PTC device, which is basically a variable resistor, and then you might have my start capacitor, okay, so I have my SC, I have my PTC device, and then I have my start winding. Okay, and this might come up to line. Questions on how this is wired? Okay. Now, there's two types of solid-state relays out there. We have a 2-wire, which is the relay only. That's what I just talked about in this last diagram. It's a 2-wire. There's one wire coming into my relay, and there's one wire going to my start winding. The other type of solid-state relay, okay, is 5-wire. It's a start capacitor, relay, and overload. All gets connected to it. Okay, and I'll show you a picture of it. I personally
Chris, can you go back? I want to take a picture of that.
This one?
No, the screen you just from. Yeah. Right. Thank you.
Okay. So, again, we have 2 wires and we have 5 wires. The screen that I just showed you was a 2-wire. A 5-wire includes wiring connections for the start capacitor, the relay connections, and the overload. When testing them out, you use your ohm meter. A good relay will have a very low resistance value when you're holding it in your hand. You must cool it down before testing. In other words, if the thing's hot, it's going to have a high resistance value. Has to cool down. A good relay will have a very low resistance value. Okay? Disconnect it from the start capacitor and the unit before you test it. You can't have it connected to anything. This is a 2-wire potential relay, or a solid-state relay. This is a 2-wire. One wire connects to either your line or your start capacitor. The other one goes onto your compressor. Okay, 2 wires. This includes a 5-wire relay. Okay? We bring our line and common in here. Okay, line and neutral, or line 1 L2 comes in here. One of these goes to my common, one goes to my run, and one goes to my start winding. Okay? So all of my connections are coming through here. You pop this apart, you find a solid-state relay and an overload right under the cap. Okay, it's called a 3-in-1. It's a 5-wire. Okay? These are really nice to have on your trucks. Okay, I carry a couple different flavors of this for the different size compressors because they're actually really nice to have. Okay, any questions on solid-state relays? Do I need to go back over anything on solid-state relays? Okay, the next device we have to talk about, because this is by far the one you're going to see most often on air conditioning, and we've already talked about this a few times, okay, but we'll go into it a little bit again here. Potential relay. It is the only relay that works on voltage. Again, let me repeat that. The potential relay is the only relay that works on voltage. It works on the voltage that is created by the start winding, okay, which is known as back electromotive force or back EMF. Basically, when you spin a magnet inside wires, which is what's happening in a motor, okay, you do create a little bit of voltage. This relay works on the voltage that is generated by the start winding. When you first have this relay, the contacts in the relay are normally closed, and it allows full voltage to go to the start winding as the motor first is turned on. Okay, so we have pins on here. Okay, what are the pin numbers I've told you about before? What are the pin numbers you see on a potential relay?
Is it 1, 3, 5, 1, 2, 3, something like that?
You're very close. The second answer was right. You're going to see a 1, a 2, and a 5.
Yeah.
Where does 5 get wired to?
Your start.
That would be 2.
Common.
Where does 5 get wired to?
Yeah, common.
Common. I just heard somebody said it.
Right.
Common. Where does 1 get wired to?
Run. Got to be the run, right?
How about either line or the start capacitor?
Oh, snap.
If there's a start capacitor, it goes to the start capacitor. If not, it goes to line. Okay? You can always tell a potential relay because of these pin numbers. And again, there's more pins up here than there are numbers, right? I mean, I count 5 pins up here. Okay, 2 of them are just connectors. They don't do anything, but you can use them to connect wires on it. Now, very important, you look at the side of potential relays. It tells you what voltages you can use, and it tells you what the maximum horsepower motor you can use. Okay, so it's extremely important you get the right relays. Don't use something that's too big. Don't use something that's too small. It won't work properly. These have a pretty wide range. Okay, another picture of them, just different number of connectors. But the bottom line is, you will see someplace written on these the pin numbers, or it will have a tag on the side that will tell you. This one, if you look closely, there's a 1, okay, there's a 2, and there's a 5, okay, and it always references something close by, some screw terminals. These 2 terminals don't do anything. They don't do anything in the relay whatsoever. They're just blank terminals you can use as wiring connections. Okay? Line to start capacitor. Start capacitor to terminal 1. Terminal 2 to the start winding. Terminal 5 to the common terminal. All other terminals are blank on potential relays. Okay? When you see them mounted, sometimes you see them looking something like this. That capacitor is a start capacitor. How do I know this? How do I know that that's a start capacitor? Just by looking at it. What's the dead giveaway of a start capacitor?
the way it's wired?
Partially the way it's wired, but looking at the capacitor itself, how can I tell it's a start capacitor? What about the case?
They don't have something to do.
It's a plastic case. It's a plastic case. Okay, 95% of the time, start capacitors are in plastic cases. Run capacitors will be in metal cases. Okay, so you can usually tell, and again, usually, because there's 95% of the time, I could tell it because it's a plastic case, it's a start capacitor. There's something else on here that tells you it's a start capacitor, and you might not be able to see it. Does anybody see what's right there? It's a resistor. Okay, start capacitors will a lot of times have a resistor between the two connections on the start capacitor. And that's the resistor will allow that capacitor to bleed off once everything is de-energized. It will actually allow this current to bleed off. Why do we want to do that? Why do I want to bleed off a start capacitor?
Take the power out?
Yeah, why? Why do I care?
I'm stuck on that.
The safety thing, isn't it? Okay, I don't want any technician or anybody to reach in there and forget that there's a start capacitor in there and get a whale on a charge and knock them on their butts. Okay, a start capacitor holds a lot of current, holds a big charge. Okay, and it will knock you over. And if you're standing on a ladder, okay, you might fall off the ladder. Okay, those things are powerful enough that it will give you a big jolt. So we put a resistor in there. It's called a bleed resistor that allows that current to bleed off. Now, do I ever trust that bleed resistor? Would I reach in there, even if there's a bleed resistor? Would I touch that thing? No. Okay, I'm still going to discharge that capacitor on my own. But the bleed resistor gives someone a better chance if they forget that there's a start capacitor in the circuit. Don't ever grab hold of anything in a motor circuit without making sure the capacitors are discharged. Okay? To check the potential relay with your ohm meter, there's an easy way to test it. Okay, if you're holding it in your hand, okay, if you're holding this in your hand, terminal 1 to 2, you should have continuity, which means your ohm meter should be pretty close to 0 ohms. Okay, very close to 0 ohms, if not 0. That's terminals 1 to 2. Terminal 1 to 5, I should have a reading that's that's in the kilo ohms. Okay, so it should be like 2,000 ohms, 1.5 thousand ohms. Okay, 1.5 k ohms. Okay, I should have some resistance reading that's up in the in the thousands of ohms. That's 1 to 5. The same reading should show up from terminals 2 to 5. So again, we look at the internal components of the potential relay. Okay, that's a normally closed contact, and we have our coil. Okay, pin 1 is over here, pin 5 is over here, pin 2 is between the normally closed and the coil. So if I go from here to here, I should have 0. If I go from here to here, I should have some resistance, okay, and it's going to be in the Ks. It's going to be in the thousands of ohms, okay? And then if I go across the whole thing, I have my 0 and my Ks together, so it should show up pretty much the same as the 2 to 5 reading does. Okay, any questions on this screen, because this is important. This is how you test these things. Most often, the cause of failure is that normally closed contact gets stuck in the open position. That's our normal cause of failure. Okay. The other cause of failure is technicians installing the wrong device. But that's just something people have to watch what they're installing. Okay. Pin 2 goes to the start winding. This is a wiring diagram. This is not a schematic. This is pictorial. Pin 5 goes to the common of the compressor. Pin 1 goes either to the power feed or to the start capacitor if there's a start capacitor. Most often when you see a potential relay, you will have a start capacitor. Okay, we don't often use them on just to cut out a start winding on a split-phase motor. You'll have a start capacitor. Okay, I use these very frequently on air conditioning systems. And I'll show you a schematic of that here momentarily. I might have to draw it. Okay. This is what type of relay is this? What am I looking at?
Potential relay. Potential relay?
Yep, again, even if it didn't say it, I see pins 1, 2, and 5. Again, this is a wiring diagram. This is not a schematic. Now, what type of motor is this? Your motor's right here. What can you tell me about this motor? We have like 4 types of motor. What type of motor is this? There's something very important here.
Was that the PSC motor?
Well, it's not a PSC. If you're looking at the run capacitor, you do have a run capacitor. What was that?
Capacitor start, capacitor run?
Yes, it's a CSCR. Okay. Otherwise, sometimes known as CSR. Okay. My capacitor my run capacitor is always in the circuit, but I also have a start capacitor. So we get the extra starting torque, but we have the efficiency of the run capacitor always be in the circuit. Okay, this is extremely important because you have an air conditioning system on someone's house that it's even a new system, and all of a sudden it starts blowing a breaker. Okay, you might have a system with only a run capacitor. You can add what we call a hard start kit, which includes a potential relay and a start capacitor. This is a frequent addition to an air conditioning system, and it will make it start better. Okay, you won't see the lights dim anymore as the air conditioning starts. So we add a hard start kit. All of a sudden, things start starting better. Okay, so again, if you have an air conditioning system where the lights are dimming, where people are complaining that it's a little bit, that it might blow a breaker here and there, especially in an older house, you can add a hard start kit. If a person puts in solar power, the solar company, the ones that install the solar panels, are going to recommend to the homeowner that they get a hard start kit put on their systems. Again, it pulls the starting amperage way down. Makes it easier to start. Doesn't put as much strain on the solar system. Okay, potential relays come with a sheet in it. Okay, and again, this is in your handouts for today. Okay, and I have this PowerPoint out there, so you can grab this. This is an explanation of the code numbers on the side of the relay. Okay, so if you have a relay type, okay, tells you exactly what it is. Okay, so if I have the letter, okay, here, it tells me it's a 5-screw L bracket. Okay? Second digit, it tells me what type of coil it is. Okay. Coil's looking for 332 volts on that start winding, slightly over whatever my voltage is. Okay, so if it's a 240 volt compressor, 332 would be about right. Okay, it tells me what type of voltage it's looking for. Okay, third item, the R. Okay, it tells me, okay, what the calibration is, what the range is. Okay, doesn't mean much to us. We can't measure that really. The fourth number or letter, okay, the fourth number, which is my last one here, it tells me the mounting position. These things have to be mounted in a certain position. Okay, it tells me how I can mount it. So again, these tags that come with these things, you get the little piece of paper in the box, you know, the thing no one reads, you definitely want to look at them. They're important. Again, wiring, okay, here as a potential relay, this comes in the box with the potential relay. It's a wiring diagram. It shows you exactly how to wire this thing. Okay, any questions on potential relays? Okay. You guys, any questions on potential relay? Okay. This comes in the box. It tells you now this is what type of thermostat is this? Are you going to wire a 24 volt thermostat in where that one says?
Thermostat. No, that's a 120 right there.
It's line voltage. You're right. I wouldn't want to wire a 24 volt thermostat in here. So again, look at these diagrams when you're doing stuff and just be careful that you fit it to your system. Okay, this is for this might be for a refrigeration system. Well, I'm not going to have the thermostat in the way there. That's going to go to my contactor. Okay, in an air conditioning system. So just be aware of that. Okay. Okay. That takes care of the start relays we're going to cover. We're really worried about those three types, okay, because that's what we see in our air conditioning window units and in our split system air conditioners. Potential relays are the one you're going to live with the most, okay? And again, pins 1, 2, and 5 are the important ones. Again, last call. Any questions on potential relays? Okay, let's talk about gauges. Okay. We use pressure in gauges to measure and display the pressure of a fluid, and I want to say, or a gas in a container, okay? Pressure gauges are one of your most important tools. There's only one tool that's more important than your gauges. What's that other tool? What's the other tool that's more important than your gauges? Your meter. Yeah, your meter. Okay? Don't ever take your gauges out of a tool bag or out of a truck without first having used your meter. Okay? And I'm going to say that several times through here. But what a pressure gauge tells me is what's happening inside a refrigeration system. And by the way, refrigeration is our cycle and is the way the system works. So it's interchangeable with air conditioning. Because again, we're moving heat from a place we don't want it to we want it. The systems are the same. It's just what we do with the air across the coils. So there's several different types of pressure gauges that function using different principles of operation. Okay, we have a lot of different ranges as well. Okay, your gauges are set up to be a specific range of readings. We can measure from a very low vacuum to up to 800 psi or higher. Some of your new refrigerants coming out are actually higher than 800 psi. If you start dealing with carbon dioxide refrigeration, you're talking in the thousands of psi's. So it's very important to know the range that your gauges can handle. The most often used operating element that the pressure gauge is used is called a board-on tube. It's a thin-walled tube of a sort of an elastic metal that's bent into a circular shape. As the pressure goes up, okay, it sort of straightens out. So it's a coil, okay, of a tube. It's basically, you have a coil of a tube. And I'll show it to you on the next slide. But as the pressure goes into that tube, the tube will try to straighten out, and it drives a needle. So again, we have our tube that's in a coil. As the pressure goes up, this tube changes shape. It tries to straighten out. It pushes outward. And that actually drives the needle that's mounted to the gear in the center. Okay? The sealed side is connected to the linkage. So again, board-on tube. Most of our round gauges use a board-on tube. Do you ever really need to know that in the field? No. Do you need to know it for your certifications exams and your licensing exams? Yeah, they're going to toss a question on board-on tube at you. So it's the part that actually changes shape inside the gauges. Now, looking at this assembly, what can you tell me about throwing these things around a truck or a car or stuff like that? Are these things really able to withstand a lot of force?
No.
No, you don't want to drop these things around. You don't want to toss these things around because these things have a tendency to break. Okay, they come out of adjustment relatively fast. Operating pressures vary in different types of refrigeration systems. Okay, some gauges use what's called a built-in retarder, okay, with the board-on tube to measure readings at a higher pressure. All this means is that once we get up to a certain point in our gauges, okay, and if you look at your gauges, those of you who have gauges already, I know our new starts don't, but if you look at your gauges, you have a place in the end of your gauge that the numbers are a little bit different. All this means is that the gauge is protecting itself. It's making sure that once the pressure readings reach a certain point, it's not going to allow that needle to slam over. Okay? So it protects, it uses a higher pressure, and it basically cuts that pressure back. Okay, after the pressure has crossed a certain pressure threshold, a retarder engages an extra spring that correlates with the gauge's higher markings. Be very careful of this. What?
A retarder?
Yeah, it's called a retarder. Okay, all that means is that it engages that extra spring. Okay, now do I recommend you ever use your gauges in that pressure area? No, it's a really bad idea. Okay, so again, down here, this is just a picture of a gauge. Okay, and if you look at your own gauges, okay, we have our standard readings, which is in the blue part. Okay, so from here all the way to here is standard readings. The green is a vacuum. Okay, this is below atmospheric pressure. And up here where it says retard, it basically says we've engaged the extra spring to protect the gauges. You're not going to get any accurate readings in this area, but your pressures are way up over what you should be using the gauge for. Okay? So if you ever get a pressure in this area, you shouldn't be using your gauges for this pressure readings. Okay, the gauge is basically protecting itself. There are three main types of pressure gauges used in our work. We use a vacuum gauge, we use a compound gauge, and we use high pressure gauges. Every gauge has a different scale, Okay, and it varies depending on the refrigerant being measured. Okay, remember our conversation about temperature pressure charts. It matters. The vacuum gauge goes from 30 inches vacuum through 0 inches vacuum. In other words, atmospheric pressure. Okay? Drops down to 30 inches vacuum. The compound gauge, that's your low side gauge. Okay, this is on my low side of my system. Most often, this is blue. Okay, if your gauges are colored, most often that's blue. Goes from 30 inches of vacuum all the way through 240 psi. The high pressure gauge, which is red, if your gauges are colored, goes from 0 psi up to 800 psi. Okay? So again, important to remember, your compound gauge will measure vacuum as well as pressure. High side gauge will only measure pressure. Okay, again, vacuum gauge measures lower than atmospheric pressure. Okay, atmospheric pressure is 14.7 psi, which would be 29.92 inches of mercury, and we don't worry about the 760 torr. I don't ever expect you to remember that. Okay, so again, 14.7 psi, 29.92 inches mercury. Okay. Now, a digital vacuum gauge is the one you're going to use most often when we do vacuum. Okay, your employer should supply these, and in our shops we supply these. Okay, because they have to be taken care of. They can't be tossed around. Okay, we measure all of our vacuum readings when we're servicing refrigeration and air conditioning equipment. We want to measure our vacuum readings in microns. Okay, that's why we use a vacuum gauge. Okay, and this is just basically a little micron gauge. Okay, you connect a hose there, and it goes in series with another component on your refrigeration system, usually a vacuum pump and then to the low side port. Okay, but again, vacuum gauge. There's different varieties of these, but they basically do the same thing. We measure in microns. A micron is equal to 0.001 millimeters of mercury, very small number. On a micron scale, a perfect vacuum is 0 microns. An increasing pressure represented by an increase in measurement. A measurement of 25,400 microns, okay, is a higher pressure than 0 microns. By the way, okay, 25,400 is about our 29 inches of mercury. So microns is how we measure microns when we put systems into a vacuum, which we'll talk about in the next series when we start talking about some more of our advanced stuff. Does anybody who's had refrigeration before remember what our micron goal is when we put the system in a vacuum?
100 or 500?
Yeah, usually 500. 500 microns. Okay. I try to go for 400 microns a lot of times if I know the system is new. Okay, but you want to be in that range and it's acceptable. Okay, it's a pretty low vacuum. We'll talk more about that. I don't want to get really caught up in that right now. A pressure drop lowers the boiling point of a refrigerant. Okay, when we have moisture in a system, we want to be able to evaporate it at a room temperature. We can use a vacuum pump to create a vacuum as low as 20 or 250 microns in the system. Again, if you get down to 250 microns, you have no moisture left in that system, you have no air in that system, and you have a really good vacuum pump. The most often number we see is around the 400 to 500 range. 250 is pushing it a little bit. Most often you'll never get there. To measure such a deep vacuum, such a low vacuum, we have to use a micron gauge. Your compound gauges cannot accurately measure deep vacuums. It shows it's in a vacuum, but it doesn't tell you how deep the vacuum is. That's why we use the second gauge. If a vacuum is drawn on a system and the vacuum gauge is reading levels of about 5,000 microns, ice or water is still in the system. It hasn't boiled off. If we can't get it below 5,000 microns, ice or water is still in the system, hasn't boiled off. Look for cold spots, look for frost, look for sweat on the outside of the system. Okay? You can use a heat gun or a thermal blanket to melt that ice. Again, we're going to go more into this when we start talking about recovery and evacuation of systems. But just know, 5,000 microns means there's something still in that system. A compound gauge, which is your blue side gauge, measures pressure above and below atmospheric pressures, also somewhat of a vacuum. It's not accurate on the vacuum side. Most gauges are typically calibrated from 30-inch vacuum to 0-inch vacuum for below atmospheric pressures. Okay? And 0 to 350 psi for above atmospheric pressures. Does the calibration last forever?
No.
No, you have to recalibrate these gauges on occasion. There's a little calibration screw in them. Okay? When you look at the gauges, the front of the gauge, the outside numbers, the one I drew my red lines on, those are our pressure and vacuum readings. Inside, you will have the temperature conversions for certain refrigerants. It saves you from having to use your temperature pressure charts all the time. You look at the refrigerant type, which I'm circling where it's shown, okay, and you can actually, for that pressure, see what the temperature is just by looking at your gauges. Do I care about pressure in the refrigeration systems, or do I care about temperature more? Do I care about pressure, or do I care about temperature?
Pressure. I think both are important.
Temperature.
I use pressure to get temperature. Okay? Pressure is a tool to get me temperature. Okay, because the pressures show me certain things. When we did our temperature pressure chart conversation, the low side pressure on my blue side tells me what the temperature of my evaporator is. The temperature the refrigerant is boiling off at in my evaporator. Okay? On the high side, which is the red gauge, okay, it shows me the temperature at which the refrigerant is condensing in the condenser. So I use my pressures to get my temperatures. Okay, that's the point of the gauges. I can use my pressures to get my temperatures. On my high side gauge, this one only shows 500, but on the newer refrigerants like 410A, which is your most popular residential refrigerant now, we can go as high as 800 psi on the high side on the high gauges. High pressure gauge. High pressures in a continuous scale. I don't often go into a vacuum on my high side pressure gauge. There isn't enough scale. These aren't set up for vacuum. High side gauge, high pressures. Always know the maximum of the pressures your gauges can handle, because you can actually exceed these pressure ratings. The high pressure gauge is usually connected into the high pressure side of the system, which is any place from the compressor discharge all the way through the liquid line. Okay, remember our 2 points of pressure change. Doesn't matter where I connect the high side of the system, high pressure gauge, but it has to be connected in the high side of the system. We have wireless pressure gauges now. Okay, I've shown you these in a picture a couple times, like my Testo smart probes. Okay, use combined pressure transducers and wireless technology, Bluetooth. Okay, I use a little sensing element, no hoses, no mechanical gauges. Okay, easier record keeping.
How much do they cost?
You know, they change frequently, but I bought mine on Amazon. If you look up the Testo smart probes on Amazon, you can find them all. And I don't get them much cheaper in the supply shop. Okay, so again, if you ever want to check them out, look at Testo, and it's the smart probe.
All right, thank you.
Okay, and you can actually find them on Amazon, and they sell different kits or they sell individuals. But that's what I use. Again, I've always liked Testo tools for measurements. You pay a little bit more for them, but again, this is one of these things, if you're using it constantly, you get what you pay for. Okay, so again, we can put pressure transducers on. Some of them have the pipe clamps right on it for taking your pressures as well, and you can use them on your phones. Okay, this is not the Testo kit. This is another brand. This is Yellow Jacket, but again, Testo basically does the same thing without any wires involved whatsoever. Okay, I really like it because it does all the temperature conversions and everything else. Okay. Some pressure gauges are specifically designed for use on certain systems or with certain refrigerants. Okay, 2 special cases where we want to worry about special gauges. Do not use your gauges on ammonia-based systems. Do not use your gauges on hydrocarbon-based systems. Okay, first of all, without special training, you should never touch an ammonia system. Okay, you can get killed and you can kill other people if you inhale this. Okay, hydrocarbon. What's important about hydrocarbon systems?
Flammable.
Very flammable. Okay, special gauges. Okay, and the other thing about ammonia, okay, is it can corrode copper. Okay, and our gauges have copper in them. It can corrode copper. So you got to be very careful with ammonia. Okay? Ammonia gauges are very specifically for ammonia, and they'll say it on it. There's no copper on this. Okay? Hydrocarbon, anytime you see the yellow on gauges, yellow means it's a hydrocarbon refrigerant. You'll see it also on equipment. You also have a little, you can probably not see it that well on your screens, but there's a little flammable material sign there. Okay, hydrocarbons. Again, we're talking yellow on the gauges. Okay, it's very obvious if it's hydrocarbon. Okay, I rarely touch hydrocarbon refrigerants. I don't like working with them. Ammonia, you just have to, depending on the size of the system, you might have to wear a respirator when you start putting gauges on and off it.
What sorts of systems use ammonia in the flammable?
Okay, ammonia you're going to find in very, very large systems. For example, I live 1.5 miles from the Florida Natural Orange Juice Factory. Okay, it's a very, very large refrigeration system. Lots of coolings, lots of big warehouse spaces. That's the type of system you'll see ammonia used in. Hydrocarbon is the exact opposite right now. Hydrocarbon you're going to see in smaller systems, smaller refrigeration systems. I'm starting to see them a little bit in window units. 18 ounces of refrigerant or less, okay, is what our current guidelines are. Okay, they're just starting to phase these in. Hydrocarbon has a problem. It's explosive. Okay, and if you get air mixed with it, you can cause what's called a flammable condition. Ammonia is very large quantities. I mean, we might be talking 400, 500 pounds of ammonia, okay, if not more. So those are the two differences. Does that answer the question?
Yes.
Okay. Both of these do require some additional training. I'm
curious though. If
what?
An ammonia, I am curious. What would you do about a leak in an ammonia system? Like trying to find a leak, because that stuff is pretty, toxic, and it gets out pretty quick.
Yeah, that's always a problem with ammonia-based systems. That's why they don't have a ton of them out there anymore. Any place where you have an ammonia-based system, you have a wind direction flag on the top of a building or on a pole. You can always tell if there's an ammonia-based system around because there's a sort of a windsock up on a pole someplace. First of all, if there's a leak in an ammonia system, you shut it down and isolate. Okay, you'll be able to see where the leak is. It's called respirator environment. Usually the fire companies are involved in this. The fire departments get involved. And they actually have to evacuate anyone downwind from the ammonia-based system, depending on the size of the leak. They do an evacuation zone. Okay, and then they isolate this. There's a lot of valves in these systems. You isolate the part of the system where the leak is at. Okay, if you're lucky, you can recover the ammonia, pump it into a different part of the system. If you're unlucky, it just goes out into the atmosphere and you have to wait, depending on where the leak is at. These are not fun things to leak seal.
Do insurance companies rate these higher? Like, is this a more expensive system to have for insurance reasons?
I have to guess on that. I don't know the answer for sure, but I would guess yes. I do know with a large ammonia system, there has to be someone on site 24 hours a day monitoring them.
Wow.
Okay.
Sounds expensive.
There are, but if you think about where they're used, that expense is outweighed by the use. Okay, I mean, if you're in a major food-producing facility, ammonia is one of the most efficient forms of refrigeration to have. Okay, it runs at very low pressures. Okay, but it's hazardous. That's the trade-off. Okay, we worry about some care and calibration of our gauges. Okay, watch high pressures. Watch rapid pressure fluctuations. Okay, and watch gauge accuracy, calibrating gauges. Okay, we got to be careful about that. Now, high pressures, part of what we want to watch at is you don't hang your gauges or put your gauges in a hot vehicle with the hoses trapping refrigerant in it. We want to make sure there's no refrigerant in the hoses that can actually raise its pressure and blow your gauges out while they're hanging in a truck. Okay? Don't leave refrigerant pressure in your gauges or in your hoses, okay, because it will actually expand and it will cause very high pressure conditions in those gauges. Okay, they make a thing called a liquid-filled gauge, okay, liquid-filled gauges, it has glycerin in it, okay, and it will actually prevent the gauges from fluttering. Fluttering means the needle goes back and forth really fast if there's uneven pressures. Okay, liquid-filled gauges. I don't recommend buying these anymore because if you're going to spend the money on a liquid-filled gauge, you may as well go to electronic gauges that don't have the needles on them and don't have the problem. But again, some of the gauges will flutter a little bit. That needle will go up and down based on changes in pressure and pressure fluctuations, especially when you start having bad compressors. Gauges calibrated on equipment, okay, will not be accurate for above or below sea level. Gauges need to be recalibrated to read 0 psi for the area in which they will be used. In other words, you need to recalibrate, you need to open up the gauges just to atmospheric pressure. The gauges should read 0 psi. If they don't, they're out of calibration. A gauge that's calibrated, for example, in my area of the country, will not work up in the Poconos or in the mountains of Vermont, okay, because they're going to be out of calibration. You have to recalibrate the gauges. Okay, electronic gauges will recalibrate every once in a while when you turn them on, as long as they sense that there's not pressure on them. They'll recalibrate themselves to 0, or you can force a recalibration. Okay, but don't forget that if you go from extreme levels of one area to another based on elevation, you might have to recalibrate gauges. Okay, to make the adjustments, disconnect the gauge so it's open to the air. There's a little screw in your gauges. Okay, a lot of times have a little hole over it through the plastic casing. Okay, that little screw, okay, well, very gently turn it and set the indicator to 0. Okay, that's how you calibrate gauges. Okay, open it up to the air so that it has full airflow where you're at. Don't have it connected to anything. Don't have the hoses connected to each other. Turn the calibration screws, set it to 0. Okay, to protect gauges, you can actually buy little protective plastic boots that goes over the gauges. Okay, therefore, if you drop them, okay, they don't bend up the casing and damage the gauges as badly. Okay, it's like the case for your phone or your iPad. If you drop it, the whole point is that it's designed not to damage the internal workings of the gauges. Questions on gauges that hasn't been asked already? Any questions? Okay, I have a question. High side gauge measures what? What does my high side gauge tell me? What does it measure?
Pressure?
Temperature.
It measures pressure, but where?
The high side pressure.
High side of the system.
Yep.
The liquid line.
Now I use it to measure, to get my condensing temperature.
Yep.
Low side gauge, what does it measure?
The density side.
The low side of the system, right? And it tells me what? What does it tell me from a temperature standpoint?
Temperature of the evap.
Temperature of the evaporator. Okay? From those readings, I can tell a lot about what's happening inside the system. Okay? There's going to be a question of the day upcoming. Probably not tomorrow, but, well, maybe tomorrow. I forget. It's going to ask, when I put gauges on a system, do I lose refrigerant out of the system every time I put gauges on and off?
Yes.
Yeah. So do you want to put gauges on every single refrigeration system?
No.
No, do not put gauges on unless you absolutely need to. Your meter's your first tool out of your tool bag. Your gauges should be your last. Okay, you don't put gauges on a system unless you absolutely need to. There's a lot of refrigeration loss, and you can introduce air to the systems.
Do you still lose refrigerant using the digital ones as much?
If I use my little digital, the little testo without that doesn't have hoses, I don't lose as much refrigerant. I mean, I might lose maybe just a little puff of refrigerant as I pull my gauges on and off, but you don't have that loss of the hoses. Okay, those hoses hold a good amount of refrigerant, and you lose that refrigerant. There's even a bigger problem. When you connect your gauges to several different systems, you can carry oil from one system to another. So if you have acid in the oil in one system, you can actually transfer that to another system by accident. Okay? So like I do a lot of insurance inspection work where I'm constantly on systems that are not working and so on and so forth. Well, using the little stub gauges that I use, the little electronic transducers, I don't have hoses that carry oil from one system to another. So you don't have as much chance of contamination. You don't have as much chance of refrigerant loss. There's just one downside to the electronic gauges, and they're slowly fixing that. Okay, the downside is that you have that you start having you can't add and charge refrigerant to the systems through those little electronic gauges. Okay, they're starting to fix that. They're starting to put charging ports on them, but right now they don't have them. Folks, that's all I have for today. Our session is just about over here. Does anybody have any questions as I'm wrapping this up?
Is there